So last time we looked at this kind of picture of basically my state 0, my state 1. After I basically set up this system and I let it run and basically release those molecules to do what they want, we are going to have this thermodynamic driving force that's going to come from, again, S configurational or delta S of mixing, which is, again, it's very similar. It's going to increase my number of configurational microstates. Our solvent will move over to the left, flow to the left side to mix with our solute here, again, to increase my number of microstates. Again, assuming that there's no enthalpic change as well. That is going to, as the solvent flows across here, my volume is going to change. There's going to be some osmotic pressure. As that volume increases, it's going to oppose gravity. Once this kind of line stops moving, we've reached equilibrium, thermodynamic equilibrium between this gravity and our osmotic pressure pi. So we want to measure or kind of get a relationship between osmotic pressure and when we're at equilibrium. And so specifically, we said we were at equilibrium when our chemical potential on our one side is equal to my chemical potential on the 0 side. So let's go ahead and derive a relationship for when that occurs and how we could kind of put that in terms of the volume of our solvent. So let's go ahead and look on the next page. So we have said that, again, osmotic pressure, we can use this to determine critical other properties of our polymers. So we can measure our osmotic pressure with our osmometer. And we're going to relate basically this to m sub n and chi. Again, we're getting a little bit ahead of ourselves, but first, let's figure out the conditions when we're at equilibrium. And that's when our chemical potential on both sides of our container are equal. So mu naught is, there's a typo here. So this is our chemical potential looking back to our previous page on the right side. So our chemical potential on the right of species 1, this is just our pure solvent. So maybe right. So this is a pure solvent. Must be equal to chemical potential on the other side. So this is our other side initially, just 1. So that's that chemical potential here, plus this additional component. Oops, excuse me. So plus this component here, where it's the change in chemical potential due to kind of this change in pressure as well. So we need to, we change this pressure is equal to that osmotic pressure. So to figure out this expression, we need to go all the way back and rethink about Gibbs. So we know that my chemical potential is equal of any system here is equal to dg dn partial constant temperature and pressure. So I can rewrite this expression. So if I want to write my partial derivative of chemical potential with respect to pressure, I kind of again substitute in this expression right here for mu sub 1, and then I could again just simplify this, take this out, and work with this expression right here. So my chemical potential of 1 is this dg dn1, species 1. So take this partial out, and I could kind of rearrange these partial derivatives. Again, it's just exchange the order of partial derivatives. So why do we exchange the order? Because if you remember back to our thermodynamics lecture, we have this expression for Gibbs. Very general, nice expression. So dg, or Gibbs is equal to u minus t, ts minus pv. So if we're at constant constant n, constant t, we will figure out dg is equal to this expression right here. Again, refer back to our kind of supplemental thermodynamic notes. Supplemental TD notes to kind of get to this expression. But if you're at constant temperature, so we're at here, and if we're at constant n, we can see that our dg dp is going to be equal to just volume here. So before we move on, we could actually, there's a little bit of a typo in here, so let me correct that right now. Excuse my right there. Oops, I want this guy. So it is plus dv. So if I know that du is equal to TdS minus pdv plus my chemical potential mu dn, and if I take then the derivative of Gibbs equals TdS minus pdv plus mu dn minus TdS minus SDT plus pdv plus vdp. That is going to, these guys are going to cancel, these are going to cancel, and then I'm left with this expression right here. So we could substitute this expression back in to the one that we looked at above here, into this expression right here, and we get this next page right here. We find that our partial derivative, again, that change in our chemical potential in our system 1. So let's look back. So the change in chemical potential of system 1 due to that change in pressure is going to be this partial derivative with respect to the number of molecules of 1, which here we just saw previously is just your volume. So this expression here is equivalent to our partial molar volume of my pure solvent. So this is a quantity that is constant with pressure. So all you have to do, plug in this expression right here. So molar volume, it is constant with pressure. So P naught plus, so your initial pressure plus the osmotic pressure. So your chemical potential is, or that change, or when we are in equilibrium, it is just going to be that difference in the chemical potential of my system 1 minus that chemical potential of my initial system, or that system in the pure solvent, that is state 0, is simply going to be this right here. A step back and actually let's think about what we're saying here. So again, this was our condition for equilibrium, basically saying that our system of state 0 and our chemical potential of my state 1 had to be equal. So this expression under here is basically saying that the chemical potential of my, or basically that the change in chemical potential between the pure and the solution side. So this is the change in chemical potential of my pure side, so state naught, so pure, and my solution side, U1, so this is my solution side. So that change in chemical potential is just simply going to be the osmotic pressure multiplied by the partial molar volume of my pure solvent. That's it. So the chemical potential of my solvent in the solution side, so with my polymer, minus the chemical potential of solvent in the pure side, that difference, the change in chemical potential, once we throw in and once we allow that solvent to mix, is just going to be that osmotic pressure multiplied by the partial molar volume of our pure solvent. That's it. Relatively simple expression. Again, that is the condition when we have equilibrium. So with this change in chemical potential, we can also relate this back to our Flory-Huggins derivation and basically look at the Flory-Huggins expression in the limit of dilute solution. So that is going to be coming next time. Let me know if you have any questions, and yeah, we'll talk a little bit more next time and get back into Flory-Huggins. We can never escape him. That's why lecture 4 was so important. So I'll see you all next time. Let me know if you have any questions. Thanks. Bye.